So here we are. You're back again after our first series has concluded. Well, I guess that just means one thing. You must really like the pain and suffering of calculus. But in any case though, we have the start of our new series in our calculus studies here on something called up here, definite integrals. But we have a few channel updates to go over together here. First off, you can email me right here directly if you have any questions you would like to have answered through video form, and we can go over it at a different time. Or you can also tune in to our live streams from Tuesdays and Thursdays from 4 to 7 p.m. PST, or you can come right in and hit us up on the chat so that you can have your questions answered live if you have something more urgent for you needed. But without any further ado, why don't we go ahead to our next segment here, which we will be talking about, again, definite integrals. So we have this one rule, and the most juiciest rule of all of calculus. It is something known as the Fundamental Theorem of Calculus. Yes, indeed. With such an amazing name like that, you can bet that this rule is the most important rule in all of the exam. And it goes a little something like this. That's what it looks like.
No.
What? What is all this nonsense? Well, let's take it through one step at a time. Indeed, we will have something over here. Oh,
What is it?
well, that is going to be something known as the limits of integration. A pretty neat thing which will let us know that if you see any of these, either number form or in some sort of variable form, those will be the feature that lets us know that we are dealing with definite integrals. All right? And so with that, we have this result here. The way you'd read this, though, is that you read it from bottom upwards. So it's going to say the integral from a to b for the function f of x dx will then turn into the new function capital F of b minus the capital function f of a. Okay? Now, there's something that you might not have noticed, but where is the plus c? Where to go? Well, that's the next issue about definite integral. There is no plus c. Not when you deal with definite integrals, not in the slightest. So just like how I was on everybody's case that you should get 0 points if you have a plus c where it shouldn't be, or in the case of the indefinite integral where you don't have a plus c, in either case, putting it where it shouldn't or forgetting it where it needs to be, in my opinion, you should all get 0 points on that problem. And so we have this idea here in which we will be practicing more and more on what this looks like in both simple problems as well as everyone's favorite word problems. That's right, you will definitely see this quite often in the free response section for the exam. But just like indefinite integrals, we will have a few rules in which we need to go over. Okay? Thankfully, though, we have some recurring ones, like, for example, the coefficient rule. Yes, indeed, that is coming back again, and will come back to us in a very special way as well. So, in a lot similar terms like before, where we have the integral, now this time, with the limits of integration from a to b, of k, a constant, multiplied by f of x dx, just like the coefficient rule before, we can simply kick it out of the integral itself, and we can deal with it after the fact from our analysis of the integral. Pretty good and pretty nice. Similarly, we have an addition rule, also very similar in kind to the addition rule of the indefinite integrals, where if we had the integral going from a to b of now two functions, f of x plus g of x, we now get to split it just like before. Of course, if you remember, we will be going up and saying I get half and splitting that integral right between the addition sign, and we end up with two separate integrals of f and g. But of course, with something to note is that both the limits a to b is going to be exactly the same for both integrals. That you cannot forget. These limits are the defining terms for this type of integral. These will not change with addition rule, but there are times in which you can change it. So we have two of the rules here for coefficient and addition rule that are both very similar, that carry over from our time with indefinite integrals. But let's get to the next two rules, which will be very unique to only definite integrals. So here we are with some of our unique rules to definite integrals, but they're fairly straightforward and will be used quite often, so they should be very well stuck into our minds. Let's get to the first one. We have the same limit rule. If it turns out that your function in the integral is going from a to a, so the exact same number, both from the starting and ending position, well, it turns out you just get to 0. We'll get more into that in detail later, but right now that's just the standard rule. Once more, if you start and finish your integral at the same exact location, you're just going to get 0. Guaranteed. Very nice. Next is that you can actually flip the limits of integration. So in this example, let's say the rule states that if your function starts from, remember, we read it from bottom to top, so it's from b to a for the function f of x dx, well, you can actually swap it back to going from a to b again, but that also means you need to hit a negative sign on the function on the outside, like a nice coefficient. So with that, we are able to manipulate the way that the function actually integrates in terms of the direction. Again, that will be useful in certain problems in the future. But right now, we just need to know that there is a rule in which we can flip the limits of integration and go on with our lives. Lastly, and I think the most interesting out of all the rules, is that we can indeed combine limits here. Okay? So in this scenario, we have the functions of two integrals here, the integral from a to b for f of x dx, as well as another function being added to it of b to c f of x dx. Okay? And that means that we can make it into one exact integral spanning all the way from a to c of f of x dx. Now, of course, there are a couple of things to note. For one, of course, is that given our letters that we used for our limits of integration, is that b is going to be in between both a and c, right? It's that little piece in the middle that we can cut out. Again, if we only go from a to b, right? If we want to do something visual here, if we go from a to b and then b to c, one right after the other, and we are adding it together, well, this rule is simply stating, well, why can't we just go all the way across, knowing that b is going to be cut out, and we will span all the way from a to c in our rule, and that is exactly what the idea is over here. Okay, and so one last thing to note, of course, is that this rule only works if what is inside of each integral are exactly the same. It needs to be exactly the same exact function, nothing different, for them to then be combined into a new function in the integral. Okay? And so with that, we just need to keep that in mind. And before you know it, we will be combining limits soon enough in certain word problems. I think this is pretty good for us to get used to for now. And we'll go over one quick example as to what this really looks like, and we'll go over some more in depth tomorrow. So let's quickly transition over to this. All right, so we have this example here of a very simple integral that should be easy in terms of what we worked on last series, but it's a definite integral, now this time going from -1 to +2 for 3x squared minus 2x. So before we go jump into any sort of conclusions, let's go ahead and take the note here off to the side to see if we do remember that nice, big, and juicy rule for the fundamental theorem of calculus. Remember that now if we're dealing with limits from a to b for the function f of x dx, then we can go and remember exactly what is the result of that, right? Just like indefinite integrals, we are going to get that new output function of capital F, but this time we will then plug in for those limits. That's why starting from the top here is f of b minus f of a. Okay? For those who have a quick eye to these differences, we read the integral from a to b because that's from start to finish, but then we will then actually write out from our equation of f of b minus f of a. So ending minus the starting. A little bit of a difference there, but it will all come to make sense at a future time. But as of right now, this is the rule that we're dealing with. So let's go ahead because we still actually need to find that capital F function as if we are doing an indefinite integral all over again. So why don't we start with that? We still need to find capital F of x for this guy here, right? The result of the integration, and then we will plug in those limits. So thankfully, now that we are all no longer diagnosed with can't integrate, we can very easily come up with the solution for this for the time being. Obviously, with our rules coming into play here, we have x raised to the third power because we're adding 1 from the exponent rule. That 3 coefficient stays, but then we need to divide by that new exponent that we just made. Same thing will go for the 2x, now raised to the second power, divided by 2 for the new exponent. Now in this scenario, we could add plus c because we're just looking for the indefinite integral for this time. But as we stated before quite clearly, this would not be an issue, as you might already see here, that we're subtracting the two functions from each other. No matter what c is, it's going to be the same for both f of b and f of a. With it being subtracted, this is no longer an issue for us. And so we can very easily cancel out some of the coefficients there. And so what we actually like to see, and what most graders would like to see, is that once you take the indefinite integral, you will set it up nice and clean like so. But then, to show that you are still going to evaluate the limits, because you can't circle this answer, we're not done. This is just the indefinite form. We have a definite form, again, definite meaning by we have defined exactly where we will start and finish this example. So you'll actually draw a nice long bar there to show that we have limits yet to evaluate from -1 to +2. A good physical reminder for what's going to happen next. So let's get this set up just like what the fundamental theorem of calculus is asking us to do. So we are going to evaluate from limit b, which is 2. If you want to make a note, again, that's the limit at 2 is b, and then the -1 is the limit at a. So let's go through this one at a time. We need to plug in as such, so 2 to the third power minus 2 to the second power. Okay, pretty simple for what we have so far. And then we need to subtract now. Quite often, I personally like to use a bracket to show that all of this is going to be subtracted. Good old order of operations still hasn't left us, even though everyone in social media loves to get it wrong. But for us, we are smarter than that. We can keep track of all of the things we need to do, and now we will plug in for f of a, the limit at a being -1. So this time it's going to be -1 to the third power minus -1 to the second power inside of the bracket, and this is how you set up for the fundamental theorem. Pretty nice. So let's go through each step here to make sure we're doing this all properly. 2 to the third is a positive 8, minus 2 to the second, which is going to be 4, minus, now inside of that bracket is going to be negative 1 to the third, which is still negative 1, minus a 1 to the second power, which is just another positive 1. Okay, very nice. So let's all put this together here, which is going to be 8 minus 4, which is a positive 4, minus all of negative 1 minus another 1, which is a negative 2. We are subtracting 4 with a negative 2. Subtracting negatives, again, very elementary. I hope no one here will get these kinds of mistakes, although I have seen plenty during my time, that a positive 6 will be the result of our integration here. Okay? So, just like all other times, we could very easily check this work as well to make sure that we have made the integral just as properly. So, just to satisfy everyone's curiosity, this is indeed a correct integral, of course, by taking that derivative of our proposed function here. Right, using good old power rule, back again, it's going to be 3x squared minus 2x, as shown in the start of the integral. So we're good there. It's just that now, if you're looking to check this last bit here of the work that's plugged in, it really is mostly simple algebra. So you can just work your way backwards to make sure that you've gotten everything correct. And so positive 6 will be the result of this integration. Isn't this a lot more fun now that there are extra steps involved in this? Well, in any case though, we'll be back again tomorrow with some more example problems that we will go into. Again, we can go just as deep as always with the complexity of integration, but we will be getting closer to finalizing all of the last ideas we need for AP Calculus, and we can get on with some actual practice problems from the older exams. Similarly to that, I'll be streaming again on Tuesdays and Thursdays from 4 to 7 p.m. Pacific time, and you can come on by and hit me up in the chat to ask if any problems that you have. Again, calculus or below, it's all good, and we can go over those together. But I'll see you again next time, and hopefully we'll get to some more complex problems. Isn't that great?